Hey guys, welcome back. So for today we are taking and looking at lesson 4. Remember you have 5 lessons this week. So let's go ahead and jump right in. So I'm gonna shrink my screen down so you can see, not making, sorry. So if we look, we are looking at Shine Bright within our lesson 4. So we're looking at diamonds. So we're looking at the weight in carats with the actual price and then the predicted price based on a scatter plot. So looking at this, when we've got 1 carat, we've got these 4 different prices. We've got the predicted price, only 1. So we've got all these different values. We've got the predicted, so with a line of fit where it should be based on the data that they have and what these actual values are. So looking here, the scatter plot shows the prices and weights of 20 diamonds together with the graph of y equals 5,520x minus 1,091. So this is the line of fit that they came up with. So this is what this is the line that they deemed the best fit for this data that they had for these 20 diamonds. So the function described by the equation y equals 5,520x minus 1,091 is a model of the relationship between the diamond's weight and its price. This model predicts the price of a diamond from its weight. These predicted prices are shown in the third column of the table. We notice that, so we can see that right here in this last weight of carats, the actual price and predicted price. So 2 diamonds that both weigh 1.5 carats have different prices. What are their prices? How can you see this in the table? How can you see this in the graph? So looking back up at the table, it said 1.5. Well, here are the 2 values. So I'm going to write this down on the whiteboard and then I'll show you in just a second so that way you can see it too. So we've got 7,474 and 5,904. So we can see that right here that there's 2 rows in the table that both show the 1.5. And then when we come back down here to the scatter plot, then what do we take and do? How can we tell that there's 2 different diamonds that both have a 1.5 carat, but they have different prices? How can we see that? Yeah, we can look at the graph and you should notice 1.5, we've got 2 different points. So let me pull my little screen back up here. So, like I said, our 2 values were the 7,474 and the 5,904. So 2 rows, this is how we know it from the table, 2 rows both have 1.5 carats. In graph, look, when x equals 1.5, there are 2 y values or 2 points plotted. So by looking at the table, we can see it, the fact that there are 2 rows that both have carats of 1.5, so we can see it in the graph. Kind of the same thing, we notice that there's 2 points for one x value, so that x value of 1.5. So that's how we can see that. All right, number 2, the model predicts that when the weight is 1.5 carats, the price will be 7,189. How can you see this in the graph? How can you see this using the equation? So it predicted that at 1.5 carats, it'd be this certain price right here. How can we tell that in the graph? So if we look at the graph right here, we've got the 1.5 is visible. I'm going to go to the screen so we can see it. So we've got the 1.5. Here is our equation, so the line of fit. So this line of fit is your keyword. This line of fit shows what the predicted value, so everywhere along this line, is the predicted value for what our price should be for our diamond. So if we look, this line of fit at 1.5 is a little above the let's see, $7,000 mark. So it's a little higher. And we know from what we did in the previous that one of our diamonds was 7,479. So we know it's pretty close, but it's just a little bit off. So, sorry, Jimmy wants to join our video apparently. Hang on. Where did that just go? Jimmy, what'd you do with my paper? There we go. Sorry, cat stole my paper. And my marker. It happens. I know. Craziness. Okay, so for this, we can tell the point on the graph. So let's see. The point 1.5 and 7,189 is on the graph of the line. So it's on that graph of the line that we have. For the equation part, so thinking back to this equation, we know the 1.5 carats represents x. So if we plug x into this equation over here, then we would find by solving this that it's the 7,189. So equation, we do 5,520 times 1.5 minus 1,091 to equal 7,189. So that's how we can tell it from the equation. It's just by plugging in what our x value is to the equation and finding what the y value is. That's how we can see that. All right, for number 3, one of the diamonds weighs 1.9 carats. What does the model predict for its price? How does that compare to the actual? So let's take a look at our model here. So looking at 1.9, so we've got 1.98, so that's a little higher, but if we look, 1.9 would probably be about here. So looking at that, it's telling us that it'll be about 900, or not 900, sorry, 9,000 and some. Now we could take and use this equation to represent that. So using the equation and plugging in our 1.9 into this, if we do that, so let me bring this back up. So if we do 5,520 times 1.9 minus 1,000, let's see, 91. If we plug all that in and find what it equals, we're going to find that it's 9,397. So this is the predicted price. So predicted. Now, if we look back at our table, at 1.9, it's telling us the actual price is 9,541. So the actual price is more than the predicted price. So actual is 9,541, predicted was the 9,397. So the difference between these, if we take the 9,541 and subtract the 9,397, we'd find that it's a difference of $144. So there is a discrepancy between these points, which is to be expected since we're doing a line of best fit. It's not going to go through every single point, so we have to keep that in mind as we're looking at these. All right, for number 4, find a diamond for which the model makes a good prediction of the actual price. How can you see this in the table and in the graph? So let's go back to both our table and our graph. If we look at this, our table, we want to find ones that are really close together in value. So let's start from the top and work our way down. So here at 1 carat, we're at 3,772 and 4,429. Not so much. 4,221, 4,429, still not overly close. 4,032 and 4,429. No. Next one, 5,385 and 4,429. Still no. For 1.05 carats, we've got the 3,942 and then 4,705. Pretty big gap there. Here we're at 4,480 and 4,705. Still a huge gap. The next one, 4,511 and 4,760. Still a pretty big gap. Here we have 5,544 and 5,533. That's a pretty small gap. It's less than 100. It's actually only 11 difference. That's a really close value compared to everything else we've been seeing. Next one, 6,131 compared to 6,085, 5,872 compared to 6,195. Nope. These ones are completely different. Once again, there's about 300 gap. These ones, there's a major gap. Look at this, 5,904 and 7,189. That's a huge difference. This one, once again, over $1,000 difference. This one, there's a huge difference, almost $1,000 difference. Huge difference, huge difference, huge difference, and huge difference, $1,000 practically. So, well, thinking back on all of those, the one that we said was the closest was the 1.2 carats. It only had a difference of $11. So we can see that in the table. By comparing the two columns in the 1.2 carat row. Now, in the graph, we didn't go look at the graph, but if we went to look at the graph, notice at 1.2, there's this point that's perfectly on the line. So that point that's perfectly on the line, that shows us that it's a very close, so the point is on the line of fit. So remember, line of fit is your keyword for this as well. All right, number 5. Find a diamond for which the model's prediction is not very close to the actual price. How can you see this in the table and in the graph? So we've had several that are very off. I think the largest one was with the 1.5 carats. So we kind of looked at this as we went through it, but the 1.5 carats, there was well over $1,000 difference between those. Remember, we had let's go back to it. We had the 5,904 and the 7,189. That's a huge gap between those. It's well over 1,000. And so we can see by comparing the two columns. And if we look at the table, it's also kind of the furthest, not at the table, at the graph. If we look at the graph, it's also the furthest point from our line of fit. So I would say the 1.5 carats, but there were a few others that we had $1,000 difference. This one was probably the most significant, and looks to be the most significant of the rest of them. So 1.5 carats, over $1,000 difference. We can see that by comparing columns in the table and noticing how far from the line of fit a point is. So using that line of fit, seeing how close our data is to one another, really looking at that and being able to use both a table and a scatter plot to analyze information and determine whether or not it's following with the predicted trend or not with the predicted trend, being able to see that. So a line of best fit, you want most of your points to be as close as possible to it. Remember, we've talked about this some, or we'll talk about this. I did the videos out of order this week, so a little backwards. But so keeping in mind line of best fit is going to best represent that data. So it should be as close as possible to all the points with still being an actual line. We don't want any crazy up and down all over the place sort of lines. We don't want that. We want a nice, perfect linear line. Makes a nice straight line. We don't want to have any crazy curves and up and down and brackets and boxes and all those sorts of things, because trying to match all those points together would not be an easy feat. There's not one line that can go through all of those points, at least not a linear one. It'd be some piecewise function we could take and go through all those, but not one single linear line. So keep that in mind. All right, that is all for today. So remember, your keyword is line of fit. Have a wonderful day and happy mathing.